Okay, well, we're going to continue with our acid-base stuff. I'm going to finish up titrating a strong acid with a strong base today. But first, a few questions about acids and bases and pH. So first of all, are strong acids always concentrated acids? No. A strong acid is the 6 strong acids that we've memorized, and then concentrated talks about its actual concentration. So if it's 12 molar or 6 molar or whatever. So a strong acid can be not concentrated, it can be dilute, like 0.1 molar HCl. Number 2, solution A has a pH of 4, solution B has a pH of 3. How does the H3O plus concentration of solution B compared to that of solution A? Well, every 1 pH unit is 10 times the amount of H3O plus. The lower the pH, the more the H3O plus. So solution A with a pH of 4 has 10 times less H3O plus than the pH of the solution with the pH of 3. Number 3, if you have a 0.2 molar calcium hydroxide solution, what is the OH minus concentration? Well, calcium hydroxide has 2 OHs in it, so that splits up into 2 OH minus. So if this is 0.2 molar, then the OH minus is 0.4 molar. And then to get the H3O plus, it'll be 1 times 10 to the minus 14th divided by 0.4 to get your H3O plus concentration. Okay, number 4, what is the H3O plus concentration in a 0.2 molar HCl? Well, that's a strong acid, so the H3O plus is the same. Why that jump? The H3O plus concentration is the same as the acid's concentration. But in number 5, in number 5, you're saying how you calculate the pH of that 0.2 molar. Then that is just minus the log of 0.2 because it is a strong acid. But what I was jumping ahead to was for the weak acid, the hydrogen ion concentration is not 2 molar in a acetic acid solution. It's a lot less than that. So how do you calculate the pH of a 2 molar acetic acid solution? You have to do an ice problem. So that is where you will set up your ice. You have HC2H3O2 plus water goes to H3O plus C2H3O2 minus. Water doesn't have a concentration. So if this was 2 molar initially, then this is 0 and 0 initially. So minus X plus X plus X, X, X to minus X. So then we would need to know the Ka of acetic acid, which is 1.8 times 10 to the minus 5th. And we would set up our, let me extend this a little bit more. Is it 0.2? There we go. And then we would set up our equation that Ka equals H3O plus times C2H3O2 minus over the concentration of the acetic acid. And that is going to be then X times X over 2 minus X equals the 1.8 times 10 to the minus 5th. And when we solve for X, which since it's to the minus 5th, we can ignore that minus x from the 2, it'll just be x squared over 2 equals 1.8 times 10 to the minus fifth. And when we solve for x, that is our H3O plus concentration. And then when we take minus the log of that, we will get our pH. It will not be minus the log of 2. It'll be a lot less than that because it's a weak acid. Okay? All right, so moving on to titration. We've already been talking about titration. That's when we take a solution that we know the pH of or the concentration of, and we're using that to figure out the concentration of another solution. The equivalence point is when we've added exactly as much H plus from the acid as OH minus from the base. That's going to be where it's called equivalence because it's equal amount of H plus and OH minus making water. We use an acid-base indicator instead of a pH meter. So we're looking for the endpoint, which is when the indicator changes color. The indicator we used in our lab was phenolphthalein, which is clear in acid and turns pink in pH 8. Again, the titration curve, we looked at this, where you have your strong acid versus your strong base. At the equivalence point, there is a pH of 7, and then we can keep adding, or we can keep trying to calculate the pH at different additions if we're not using a pH meter. So that's what we're going to do. We're going to do a problem where we can calculate the pH after different amounts of base are added. Indicators, we've talked about using phenolphthalein. We could use other indicators, or we would have to use different indicators if it were a weak acid or a weak base titration, which we'll get to later. The whole idea of the indicator is that it itself is a weak acid or a weak base, and so it changes color when there is a hydrated form versus unhydrated form. And when that ratio is 10 to 1, then you can actually see a color change. So like with the one on here, this indicator happens to be yellow when it's acidic, and it turns blue when the hydrogen's been donated to water. And when there's 10 times more of the acid than the base, it would look yellow. When there's 10 times more of the base than the acid, it would look blue. But we'll come back to that later because we just use phenolphthalein in our titration. Okay, so this was a problem. Oops. Sorry. That we have. So we want to be able to calculate the pH at different points in the titration of a strong acid with a strong base. So we're going to calculate the moles of H plus and the moles of OH minus that have been added and react them. And then we're going to determine the pH from whatever is left over. Remember, molarity times liters equals moles. Okay, important. Molarity times liters equals moles. So we have to do that for our HCl and our NaOH. Okay, so at the beginning, you have 25 milliliters of 0.1 molar HCl. Okay, so what's the starting pH? So all we have in there is HCl. It doesn't matter really at this point how much there is because it's 0.1 molar. So if it's 0.1 molar HCl, then we know our concentration of H3O plus is also 0.1 molar because it's a strong acid. So for that, now we just take the pH equals minus the log of 0.1, and we see that we have a pH of 1 to start with. Okay, so just our 25 milliliters of HCl, the pH is 1. If we were doing the pH curve, we would be right down here at the beginning, starting at pH 1. That's where our acid is. Then we're going to calculate the pH after we add some NaOH to it. So we're adding 10 milliliters of 0.1 molar NaOH. This is where you have to do this calculation in moles. Okay, so the calculation has to be in moles. So we have 0.025 liters of 0.1 molar HCl. So that means we have 0.0025 moles of HCl, which there's one H in HCl. It's a strong acid. So that means we have 0.0025 moles of H plus. Okay, liters times molarity to get moles. We're adding 10 milliliters of 0.1 molar NaOH. So 0.01 liters, changing our milliliters into liters, times 0.1 tells us that we've added 0.001 moles of NaOH, which is the same thing as adding 0.001 moles of OH minus, because it's a 1-to-1 ratio. Now, H plus always reacts with OH minus, so that means the 0.001 moles of OH minus is going to react with the 0.001 moles of H plus, and now there's going to be leftover H plus because I had more H plus to begin with. So 0.001 moles of my H plus gets reacted, and I have 0.0015 moles left, but for pH, I need molarity. So now I go back and divide by the total volume. Okay, I had 10 mils of NaOH added to 25 mils of HCl. So my total volume is 0.035 liters. So my H plus concentration is now 0.0015 divided by 0.035, and this is my new concentration of H plus. So now my pH will have gone up a little bit. When I take minus the log of that, I get 1.37. Okay, so my pH is starting to go up as I'm adding base. That makes sense. Okay, next, I'm going to continue to add NaOH. So again, I have 25 mils of acid still in there. That hasn't changed, but now I've added more base. So I still have 0.0025 moles of HCl, 0.0025 moles of H plus. Now that I've added 25 mils of NaOH, I've now added 0.0025 moles of NaOH, which is 0.0025 moles of OH minus. Again, H plus always reacts with the OH minus. So those two are going to completely react, and that means there won't be any OH minus left over or H plus left over. They're going to completely react. So that's going to be a pH of 7, okay, because I had 0.0025 moles of H plus that was neutralized by 0.0025 moles of OH minus. Complete reaction. Okay, so that would be a pH of 7. I would be at the equivalence point. Now, if I keep adding more NaOH to that, now it's going to get more basic. So at the beginning, I started down here. I was adding. I just got up to the equivalence point. Now I'm going to keep adding base. So the pH is going to keep rising. Okay, and then it'll eventually level off again. So with the same process, I start with how much HCl I had, still have that in there, still have that many moles in there, but now I've added 35 milliliters of the NaOH. So now I'm adding 0.0035 moles of NaOH, which is 0.0035 moles of OH minus. Again, they're going to completely react together, but only 0.0025 moles of the OH minus will be reacted because that's all of the H plus I have. And so when I subtract that out, what I'm going to have left is, let me move this out of the way if I can. That was my pH curve. Okay, so what I'm going to have left now is 0.001 moles of OH minus left over. So to calculate pH, I need H3O plus concentration. So I will subtract out that, and I got that, OH minus. So now I need to divide that by the total volume, which is 60 milliliters because I added 25 milliliters of HCl to 35 milliliters of NaOH. Well, I added the NaOH to the HCl, but either way, I had 25 of that one, 35 of that one. So there were 60 milliliters added together. So my new volume is 0.06 liters. So the moles of OH minus left over divided by its liters gives me my new concentration of OH minus. So minus the log of that gives me a pOH of 1.77. Okay, so my pH then will be found by subtracting that from 14. So my pH has jumped all the way up to 12.23. Okay, so it'd be way up in the base because I had excess base. Okay, so that was your titration of a strong acid with a strong base. They completely react. They make water and a salt, whatever's left over of the ions. So in this case, it would have been NaCl with water are the products. And that is the end of that. I thought I would show you a joke about acids and bases. Always got to have a joke. So this is a baking soda with a lemon, and it says, "I'm tired of your sour mood and your acid sense of humor." That's the baking soda, the sodium bicarbonate talking. And the lemon says, "If I had your base personality, I'd be bitter too." Remember, bases taste bitter, acids taste sour. And the salt says, "Ouch, that's pouring salt on a wound." So it's kind of a little cute joke about acids and bases and their properties.